Hello, how are we all? ¿Cómo están, mis amigos? Hey. Yo aprendo con Duolingo todos los días, 5 minutos en albanos. Disculpa, lo siento. Okay, I'm going to switch back to English where I can be even more embarrassing. So I'm very surprised that so many of you would come for a title which is so boring. So well done to you for being at the end of the day coming to a talk with an extremely psychopathically boring title. La lucha continúa, the struggle continues. This is a story which is unfolding. So I'm going to talk a bit about distributed systems, fault tolerance, transactions, all that kind of fun stuff. And I can't believe the warm welcome that I've had since I've been here. I come to Spain several times a year for holidays and for business purposes. And at this conference, it's just been an exceptionally warm welcome, being in and out of some sessions today. So we started with Michal in the wonderful shirt, Michelle, we'll come to Michal momentarily. I was distracted by your shirt. Michelle, who basically said, this is a done thing. Here are my 2 books. So that was nice. So I've got nothing to say. And then Michal gave a splendid talk about how Red Panda have been talking about Raft, leaving me basically no intellectual headroom left to give this talk. Then Sean was like, we're going to kill all the databases. It's like, holy shit, I'm the database guy. How much warmer can this welcome get? And then you poor people are stuck with me between now and drinking and singing, which is terrible. Anyway, it would be impolite to leave now, right? As a Brit, that kind of thing would give me significant anxiety. I don't know how that translates into Spanish, but you're stuck with me now. We're kind of like hostages. So what am I going to talk about? A bit about graphs, because I work for a database company that specializes in graphs. I'm going to insult you by telling you that programming is too easy. I'm going to ask you whether you think distributed programming is too easy. I'm going to tell you why we shouldn't do distributed computing, because the theoreticians have already demonstrated it doesn't work. Then we'll think about coordination, making it scalable, and then we'll zoom off into the future and then get some beers and karaoke. Good plan? Yeah, I reckon so. Okay, this is where I live. Actually, I live a bit further south, but this is my universe in London. And you are cordially invited to come and visit me in London, and you will land here at London Heathrow. And my office is here in a place that to the Americans looks like it's called Southwark. And we call it Southwark. That's just to mess with the tourists. So we live here in Southwark. And the question that I give to you fine folks is, how would you get there? And of course you already know, right? You already know the rules of this diagram, right? You know that you can go from dot to dot on this diagram, providing there's a line between those dots. Because although this is definitely a diagram of the London Tube network, the London Transport Network, it's also a graph. So humans are quite good at understanding graphs. And we know, for example, one permissible route is to take a lovely long ride past Wembley Stadium, round through the financial district, cross the river, and then arrive at Southwark. But you intrinsically feel that's a bad route, right? And you're right, of course. That's not the shortest path. The shortest path, if you run Dijkstra or something, as Michelle mentioned earlier, Dijkstra already solved everything, is to come up this blue line, change onto this silver line at Green Park, which is where King Charles lives, and then take the Jubilee line down to Southwark. Everything on this diagram sounds like Harry Potter, I just realized, right? So that's graphs, and I work in a graph database with the labeled property graph model, and it's really simple, right? We have nodes with relationships between them, and those nodes are like entities, and they can have labels that tell you the role of the entity in the network, and the relationships tell you how those nodes interrelate. And you can put data on them. That's it. You don't need to read all 1,200-odd pages of Al-Masri Nafvi, even though it's a brilliant book. You can just read that book that me and Jesus Barraza wrote recently, grab a free copy from Neo4j. And what that means is you can write queries like this that are quite liberal about associativity. So this is actually a very simple recommendation query. It's saying, hey, database, find me a pattern where I've got a customer node that has an outgoing friend relationship at depth 1 or 2 to another customer where the customer's name is Alice and the customer isn't their own friend because friend of friend could be me. With that customer, tell me this pattern, find me matches for this pattern where I've got a friend who bought a basket which had some product in it and tell me the results of that in descending order limited to the top 5. Tell me the top 5 products that my friends and friends of friends have bought, right? Wow, you're now graph database experts, by the way. I bless you. St. James of graphs. But what's really interesting from a distributed systems point of view is these relationships, right? Because they can do all kinds of crazy things like span machines. And when things span machines, it gets complex and interesting. These relationships can be traversed, read in either direction, and they should be traversed or read in either direction at the same cost. In a social media example, in a Twitter kind of example, if I follow you on Twitter, you should know that you are followed by me, right? That should be implicit. It's no good that I know that I follow you, but you think I don't. That's corruption. So because these relationships can, in theory, span shards, we have to look after them, and we have this special thing down here called reciprocal consistency. If I follow you, you know you are followed by me. And that often means changing 2 records on 2 completely different machines at the same time whilst preserving atomicity. Kind of interesting, right? So, we'll get to that, but first let me insult you. Again. Now, some of you have heard me talk before. Someone's smiling at me from the audience. He knows what's coming. Programming is too easy. Yeah? Your jobs are trivial. The electronics engineers have done all the hard stuff, and let me show you why. This is programming, right? So I've got some kind of Java-ish pseudocode here where I set the value of variable I to 10, then I set it to 11, and then I print out the value of I, and I get 11, right? Everyone agrees with this. Yeah? This is mad, because under the covers, your computer, this MacBook here, is doing all kinds of crazy stuff. It's doing out-of-order execution. It's doing branch prediction. It's moving things around cores. It's got something like kind of cache consistency, cache coherency protocol running. It's mental, and yet it still prints the correct answer, right? Oh, wait, what? Excuse me? Oh, that'll fix it. Thread.sleep 2000. It's twice as good as thread.sleep 1000. That is from my distributed debugging box of tricks. Come to my course. What? Now it says 11. No, it says 10. Holy crap. Imagine if your computers really did work this way. They don't, of course, because, as I said, the electronics folks have already done a bunch of hard work for us. They give us these things that compilers use called memory barriers. And what it makes sure is that the sequential ordering that we see in our code is a sequential ordering that we perceive when the code is run. So we don't have to worry about all the crazy that's going on in our many-core computers. And I think that's a big relief, right? Because if you had to program a many-core computer at its true nature, which is a distributed system in a box, it would drive you crazy, right? I much prefer this abstraction. So, distributed systems are cool. Who likes distributed systems? Yeah, some waving. Cool. Who dislikes distributed systems? Yeah, thank you. Yes, you're both right. The correct posture with distributed systems is the kind of Schrodinger posture. You like them, but you also hate them. And it depends on the day, right? You might feel like a genius, or you might feel like a fool. And that's the way distributed systems make you feel. Now, I should tell you, I'll tell you a personal story. I'm the first person in my family to have any qualifications. Like in my whole ancestral tree, nobody has any qualifications, and then I turn up, right? And so I go to school, and I don't get kicked out, and I get some qualifications, and I go to university, and I get an undergraduate degree, and that's good, and then I do a PhD. And I've got to tell you, my mum thinks I thought that I was wonderful. She was just like so proud of me, right? And we're like a very working class family, and she like gossips to all her mates about how clever her son is and all that kind of stuff. And I'm not trying to flex, because this is where it gets sad. So she said to me once, hey, you've got all these qualifications, and I have to call you doctor now and all that stuff. What do you actually do? I said, well, Mum, I work on this problem called consensus. She's like, yeah, that sounds good. That sounds technical. What does that mean? Well, like, if I store a number in one computer, and she's like, what number? I don't know, Mum. Like, 6? Yeah, that's a number. Okay, 6. So if I store the number 6 in one computer, I make sure that the number 6 is also stored in a nearby computer. And she looked crestfallen. Oh. That hurt. I have to say that, oh. Such disappointment, right? Because it sounds like such a trivial thing, right? You put 6 in that computer, and you put 6 in that computer. And how many years at university to do that? Because, of course, she doesn't see all the clever, frustrating, maddening stuff. That stuff goes wrong, and when you're trying to put right stuff that can go wrong, other stuff goes wrong when you're doing that. And everything goes wrong. It's all on fire. It's like a huge garbage fire all the time. So you're right to like and dislike distributed systems. This is how many distributed systems look. So I need to log in to continue my purchase. Cool. That would work. Or I can register to continue my purchase, and then no account found. Wait, what? Run that by me again, Jim. So I need to create an account, so I'm going to register. I register, and then I use those credentials, and then I log in, and no account found. Wait a minute, that's a bit annoying. That's some kind of user interface fail? Well, it's even worse, right? Because if you put thread.sleep 2000 in, then it works. That's ice cream, obviously. I wouldn't dare put a picture of a poo in front of such an august audience. That's shit, isn't it, really? Distributed systems are horrible because they make you do this. Thread.sleep will make it work. This is horrible. Why? Oh, my word, this is insane. And the reason is because distributed systems are hard. There's all kinds of concurrency and race conditions, and it's hard to control them. We don't have memory barriers. And the reason is because of these folks, right? These folks, Fisher, Lynch, and Patterson, FLP. Who knows CAP theorem? Who remembers arguing about CAP theorem a decade ago? Who now realizes the pointlessness of those arguments? Thank you, sir. Actually, these guys predate CAP theorem by a long time. And since I only have a few minutes, I'm going to shorten what it says in this paper. But basically it says, distributed systems don't work. You can't make them work. Tough shit. That's basically what it says. It doesn't work. You can't make them work because there's always the possibility that you'll have one faulty process, and that one faulty process ruins everything. Now, the bit that they don't tell you, the subtitle is, things often go well enough for long enough that distributed systems can be useful. But in general, there is no way a distributed system will work in the general case, is what this paper tells us, right? Which is a really kind of depressing paper. But it's a great paper, right? Because it teaches us about this trade-off between availability and reliability, which is a very fundamental thing in distributed systems. So I can be available even when things are going wrong, as long as I'm prepared to give the wrong answer. Or I can choose not to be available when things are going catastrophically wrong. But you know what? I'll probably always give the right answer. And that's what FLP teaches us. And in practice, it means that for some systems, for some use cases, you can get away without using any coordination. You can fall back on things like, base or eventual consistency, which, again, what the subtext there is no guarantees whatsoever. Or sometimes you need to use systems that are correct, and you will need to coordinate. And I think with coordination, you're kind of damned if you do and damned if you don't. And in building Neo4j, we chose to coordinate, so we're damned if we do. What we use in Neo4j is Raft. So, Michal, this is very much on the same territory that you were on earlier. And we chose Raft after having an earlier implementation of Paxos. And one of the things with Paxos is, at the time, Neo4j had about 20 engineers. We were quite small, and we had greater than 20 opinions on how Paxos works, right? And I don't care how many times people tell me the part-time parliament made simple. No, Paxos is not simple. It's dressed up in all kinds of fruity language that makes it hard to understand for even intelligent people. We love Raft because Ongaro and Oosterhout being the tickle guy, right? And like a complete polymath and awesome person, and Ongaro being a complete sweetheart, they just said, no, let's just do everything on the simple level. Because in distributed systems, complexity is where the tricky bugs hide, right? And in a distributed system, we don't want clever things where the bugs hide. And I certainly don't want to dress it up in Greek mythology, because that adds more layers of like, what the heck is going on here? I want something that's understandable. And this paper, very much in common with Michal, was the thing that we read. We were like, we understand this now, and we all consistently understand it, and we can build it. So what's going on in Raft, what's going on in Neo4j, is that we have these servers, and one of the servers at any given point is playing the role of a leader or a coordinator. It's actually imposing an ordering, A before B or B before A, and it's asking the other servers whether they agree. And when a majority of the overall servers agree, we can consider that an entry has moved from being appended or at risk in the log to being committed and safe in the logs. It's multiply redundant. RAF's lovely because the leader can move, so if you get failures in the system, the topology of the system is baked into the log, and so you can just pick up, elect a new leader, and carry on going. And so it's a really nice protocol. I very much recommend, if you didn't see Mihal's talk, catch it on the after videos, because it was really lovely. But RAF keeps logs tied together, so it's a lovely metaphor, and in a database that makes a bunch of sense. Keeps entries both for your data and for your cluster data, and the model is that the leader, the proposer, it sort of sends out requests for others to persist records. If they say yes, then inductively their logs must be the same all the way to the current index. Now, the three sort of states, if you like, in Raft: appended, where you add something at the end of the log and it's at risk; committed, where the Raft log the entries are now permanent and durable, even in the face of failures; and in our world, applied, where we take what's in the Raft log and we apply it to the database to make changes in the user's model. Now, cluster members are always ahead or behind of each other. This is perfectly normal, even in a transaction protocol or consensus protocol that provides strong guarantees. This is normal behavior, but it does have some interesting impacts. So remember, Raft provides strong guarantees to strong consensus protocol. I can see logs here, right? I can see ordered sequences that are agreed upon by many machines. So let's see what happens when I try my register and login example. So I go and create an account. An account gets created, so I can see that entries are being appended into the log. Majority responds, and then I can assume that we are now safely durable. So I'll use those newly created credentials to log in. And of course, now because we're using this strong protocol, what's going to happen is, it hardly seems fair, does it? We've done all this work. We've got logs, we've got a cool protocol with like a computer science paper and everything, and we've still got this. And the question is why? Why wouldn't we just do thread.sleep 2000, thread.sleep 5000? Why? Actually, it's because this is normal behavior, and Raft doesn't account for this. Raft actually explicitly leaves it as one of the Raft's cute little behavioral issues, which is Raft works in terms of simple majorities. If enough of the members of your cluster have agreed, then a minority of those clusters might not yet have agreed, although they're pretty likely to agree in the next few milliseconds. So there's a little race condition there. What we do in Neo4j is we build a causal layer on top of that. It's very straightforward. We call them bookmarks, even though they're definitely not bookmarks. I work for a badly named company. We name things badly. That is what we do. So instead, what we do is when we write something into the database, we get a little opaque set of bytes that's effectively the transaction ID, and then we can use that when we subsequently read from the database. And what will happen is that if we land on a machine that hasn't yet processed that transaction ID, we'll just hold up that query for a moment until that entry has been committed and then applied into the database. Then we can safely run the query and you get the correct behavior, which is good because now the database acts like a variable, right? Even if it's spread across a WAN, right? You've got this nice causal layer that means it behaves very much like int I in your programming language. But from a performance point of view, you've got this leader that's always coordinating the followers, right? And that can lead to all sorts of fun things, right? You've only got one of them for a start per RAF group, and then you get things like jitter as you get elections and so on. Then you've got to try and tune your elections. Half a second, is that good enough? Well, that might be too aggressive. Okay, 10 seconds. Well, then if something does happen, I probably have to wait a long time before the leader picks up. There's all kinds of interesting things having that. So I think we can improve coordination. So this is the other door. This is damned if you don't, right? So correctness, particularly for graphs, requires coordination. Otherwise, one transaction can be deleting a relationship while another is updating property values on that relationship. And if you're doing this across shards, you have the potential for them to be done in the opposite order. And if they're done in the opposite order, the outcome is corruption. And that's bad, right? You don't preserve reciprocal consistency. But typically, coordination is thought of as slow, right? So for those folks in the room, particularly the mad waving guy over there, who I love, he's one of my favorite audience members now. If you've done things like two-phase commit, like the old guys in the room, I'm not picking on Sergey at all, but I know he's done this. We think about two-phase commit, he's speaking last tomorrow, he can get his revenge in then. We think of two-phase commit as a slow protocol for enforcing unavailability, right? We don't like that. That sounds like horrible words for a high-performance distributed system. And in fact, we typically force coordination all the time, even in those cases we don't need it. Now, as I mentioned, the big challenge in graphs is that we have to preserve reciprocal consistency. So what can we do to make sure we preserve this constraint while doing things in a not-so-bad way? Well, we need to do a bit of computer science, would you? Come on, Alan Turing? Can you not see the resemblance? I mean, not intellectually, obviously, but okay, fine. So good things, right? So there are good things happening. This is from a paper from Heidi Howard a few years ago now when she was at Cambridge. She's now at Microsoft Research. And her research shows that you don't need to have a majority for your quorums. In fact, you can have less than a majority of quorums using all kinds of fancy shapes like trees and tables and rows and all sorts of stuff. And that means you can have a minority of servers in your cluster answer and still get certain safety guarantees. Now, of course, there's no such thing as a free lunch. In those worlds where you've got fancy shaped quorums, when recovery happens, when crashes and recovery happened, it's no longer homogeneous, right? So different recovery strategies based on where the failure is. I'm not a big fan. I mean, I love Heidi's work. I think it's intellectually incredible. But I think when I've got a failure and the stress is on, right, because I need to return service or whatever, I don't want to be thinking anything about different machines, right? The machines all need to be the same and easily replaceable. But it's a thing. So we can do less clever thing, we can involve less people, less machines in terms of voting. The other thing we can do, which is Baylis and my old fairy godmother, Alan Fekete, when I was at UCID, they said, actually, you don't need to coordinate all the time. So they looked at the TPC-C benchmark, and they said, well, oh my goodness, only 13% of these transactions actually need coordination. The rest can run like on some fast path without coordination. 87% of the transactions can simply run uncoordinated. So they came up with this idea of coordinate where you have to for correctness, but a lot of things you don't have to coordinate about. And these things have kind of sat bubbling around my brain. But there is a common theme here, right? So the theme is the coordinator. And having the coordinator, one coordinator, remains problematic. So can we do better? We can do smaller quorums, we can coordinate less, but if we still have one coordinator, that's a problem. So let's see if we can make coordination scale. Now, back in the day, like in prehistory, there were these things called chain replication protocols, right? And these aren't fancy. They're just basically like a linked list of servers, and you put data in at one end, and the data replicates through the chain, taking data from the upstream server and passing it to the downstream server so that you get some kind of replication. Not super popular, because it's not hard to see what happens when a server in the middle of the chain goes away, right? Replication comes to an abrupt halt, and then you've got to do complicated repair and stuff. So I'm not at all a fan of chain replication protocols, but this idea of chains can have some really interesting properties. So, for example, this is from a paper called Warp, which is much, sadly, overlooked. But Warp provides one copy, serializable ACID transactions with no spurious coordination. That is to say, it does transactions properly, and it doesn't waste time doing coordination where it doesn't need to. I mean, you say 5 minutes, I reckon I've got 10 left, but we can negotiate and I've got the mic. So, what about if we went from chain replication protocols to chain transaction protocols, right? So we could kind of do something where the outbound, so when we go down the chain, that's kind of the equivalent of the commit phase in two-phase commit. We hit the last server in our set of shards or whatever, and we come back doing commit, right? Cool. But you could say, Jim, isn't that just the same as two-phase commit, but just like more fragile? And shh, don't interrupt. I knew you'd be thinking that, because you're smart. That's why I had to put this slide in, just to give myself a chance to think. It's not quite. It's actually underappreciated genius. In the single case where you've got one transaction, definitely, it's the same as two-phase commit, right? Why would you bother? But any competent system isn't running one transaction at a time, right? It's running many. And that's when things get interesting. because ordering is typically a problem that is solved by the coordinator. But what instead if we federated coordination into this network? So here I've got two transactions running, one from Rosa and one from Carl. And you can see that Rosa and Carl, they contend on shard 1 and on shard 3. Well, wouldn't it be nice if actually shard 3 just says, look, I've got these two concurrent transactions, and I'm going to pick a commit ordering. I'm going to toss a coin. Because it doesn't actually matter whether it's Rosa or Carl first, provided everybody else does the same. So I'm going to flip a coin, and I'm going to say Carl. And now every other shard that has Rosa and Carl, make sure that they commit Carl first, then Rosa. And that's lovely because then any one of these machines can effectively act as a mini coordinator. So on the forward pass, Carl continues on, Rosa comes back. Makes sense for it to be Carl, and you'll see, you'll see that on the backward pass, anywhere where Rosa and Carl contend, Carl goes first, then Rosa. And in fact, in keeping with the Bayliss and Fekete paper, where they don't contend, just run them in parallel. Right? Why bother putting machinery in the way? Just let it run through the fast path. So don't coordinate where you don't have to. So I think this is really underappreciated genius in distributed systems. The fact that we don't have to impose a total ordering everywhere with a coordinator. We can impose a partial ordering that can still be safe at much lower cost and be able to federate that through the network. It's absolutely a brilliant idea. I'm very much in love with it. Now, of course, the thing is you could mix these things. Chains can get quite long and unwieldy in a large system. So what you might want to do is use something like Raft to create shards or replica sets, and then connect the leaders of those replica sets with a chain to keep it a bit less unwieldy. But what else can we do? So where we're going, we don't necessarily need leaders. So we can use chains across shards, chains for inter-shard coordination, but we don't have to. Admittedly, this is probably more me than Alan Turing, but there is an emergent idea that Tobias Lindorker of Pinecone and myself are working on, which is to say, actually, the metadata in our messages can be used to coordinate. So we had this idea called conjunction of majorities, and it was originally designed to solve some Neo4j problems, but it seems actually very general. And this idea is that each participant in a cluster has a DAG of its ancestor transactions, the ones that have committed, the ones that are committing, the ones that are prepared. And each transaction can turn up at one of those machines and say, these are my ancestors. Do you have a compatible DAG? And compatible may mean identical, or compatible might mean, actually, you've got some transactions in the pending state that I know are committed because the majority committed elsewhere. And once they're committed, are we now compatible? And we think this makes a really interesting scalable system because you no longer have a single coordinator. Any machine in the network can coordinate, and they simply transmit their expectation. A transaction takes its expectations of a version, a state in a server with it, can be cheaply compared, just like e-tags in HTTP, to see whether the transaction can commit or not. If you have enough transactions committing, you have a majority of transactions committing in a shard, and then in all of those shards can commit, you've got a conjunction of majorities, and you commit straight away. This is work in progress. Like we have a prototype that's kind of half built, and we're running it through some tests. We're going to integrate this with Neo4j and run it through the standard battery of Neo4j tests, and we're optimistic we can do some really fun things with these. So look, I hope that Whistle Stop Tour was fun. I wasn't much more than 5 minutes, hopefully. Thank you for listening. Look, this is an amazing field. Please do come and talk to me so that I don't have to do karaoke later. Also, if you're interested in Neo4j things, grab a copy of that book and have fun graphing. Thank you very much. Enjoy your evening.